In section 5.3, we look at the rational numbers. So if two integers are added, subtracted, or multiplied, the result is always another integer. This is, however, not always the case with division. In order to permit such divisions, we enlarge the set of integers, calling the new collection the rational numbers. The set of rational numbers consists of all the numbers that can be expressed as a quotient of two integers with the denominator not 0. The set of rational numbers is the set of all numbers which can be expressed in the form a over b, where a and b are integers and b is not equal to 0. The integer a is called the numerator and the integer b is called the denominator. In general, every integer a is a rational number because it can be expressed in the form a over 1. A rational number is reduced to its lowest terms or simplified when the numerator and the denominator have no common divisors other than 1. Reducing rational numbers to lowest terms is done using the fundamental principle of rational numbers. If a over b is a rational number and c is any number other than 0, then a times c over b times c will just become a over b. And we call these equivalent fractions. When using the fundamental principle to reduce a rational number, the simplification can be done in one step by finding the greatest common divisor of the numerator and the denominator, and using it for c. To reduce a rational number to its lowest terms, divide both the numerator and the denominator by their greatest common divisor. So we want to reduce 130 over 455. So we need to find the greatest common divisor first. So 130 can be broken down into 10 and 13. And 10 can be broken down into 2 and 5. And so we get 2 times 5 times 13. Let's do 455. 455 can be broken down into 5 and 91. And 91 can be broken down into 7 and 13. So we have 5 times 7 times 13. Now the greatest common divisor is where we take whatever's common to the lowest exponent that's present. So they both have a 5 in common, and they both have a 13 in common. Times 13 is 65, and so that's what we want to divide out of the top and the bottom. So 130 divided by 65 is 2, and 455 divided by 65 is 7, and so our new fraction is going to be 2/7. A mixed number consists of the sum of an integer and a rational number, expressed without the use of an addition sign. An improper fraction is a rational number whose numerator is greater than its denominator. So to convert from a positive mixed number to an improper fraction, you're going to multiply the denominator of the rational number by the integer and add the numerator to this product. You'll place the sum in step 1 over the denominator in the mixed number. So let's convert 3 4/5 to an improper fraction. So we take the denominator, 5 and we multiply it by the big number, which was 3, and we add the numerator, which was 4. And we put this all over the original denominator, which is 5. Well, 5 times 3 is 15. And 15 plus 4 is 19. So we end up with 19 over 5. Now if I want to go the opposite way and convert our improper fraction to a mixed number, we divide the denominator into the numerator, we record the quotient and the remainder, and then we write the mixed number using the following form: the quotient and then remainder over the original denominator. So we are going to do a long division problem. We put our 5 on the outside and we put 42 on the inside. 5 goes into 42 8 times, and 5 times 8 is 40. (42 minus 40 is 2. So the number that's on top is your quotient. The remainder is what we have left over, which is a 2. And then the original denominator was a 5. When converting a negative improper fraction to a mixed number, we just copy the negative sign and then follow the previous procedure. So just leave it for the end and then just kind of put it in front. We have seen that a rational number is the quotient of integers. Rational numbers can also be expressed as decimals. Any rational number a over b can be expressed as a decimal by dividing the denominator b into the numerator a. So we want to go ahead and express the rational number as a decimal. 5 over 8. So again, we're going to do a long division problem. We put our 8 on the outside, and we're going to put our 5 inside. Now 8 does not go into 5, so we need to put a decimal point and a 0. So 8 doesn't go into 5, but does 8 go into 50? It does go into 50. It goes in 6 times. 8 times 6 is 48. And 50 minus 48 is 2. What we want to do next is draw another 0. And we're going to bring it down. Does 8 go into 20? 8 does go into 20 2 times, and 8 times 2 is 16. 20 minus 16 is 4. And then we're going to repeat the process. We put another 0, and then we're going to bring it down. Does 8 go into 40? It does go into 40. It goes in 5 times, and 8 times 5 is 40. And so when I end up subtracting this off, I get a remainder of 0. And so 5/8 is really 0.625 in decimal form. Let's go ahead and try 7 over 11. It's going to be the same method. We put our 11 on the outside, and then we're going to put 7 on the inside. Now 11 doesn't go into 7, but 11 goes into 70 6 times. 11 times 6 is 66. 70 minus 66 is going to give me 4. And then we do the same thing that we did before. We put a 0 and we bring it down. How many times does 11 go into 40? It goes in 3 times, and 11 times 3 is 33. Minus 33 is going to give me 7. We're going to put another 0, and then we are going to bring it down. How many times does 11 go into 70? It goes in 6 times, and we end up getting 66. So when I subtract off, I end up with 4. And we just repeat the process again. How many times does 11 go into 40? It goes in 3 times, and we end up with 33. And when I subtract that off, I end up with 7. Do you see a pattern that's happening here? Whenever I subtract off, I'm either ending up with a 4 or a 7, and it keeps alternating. I'm never going to get anything else. So I'm just going to keep repeating between 6 and 3 and 6 and 3 at the top. And so we call this a repeating decimal. And we write this as 0.63, and we put a bar over the part that is repeating. So the first one of 0.625 is called a terminating decimal because it ends. The other one, where it was 0.636363 forever and ever, that is a repeating decimal. So any rational number can be expressed as a decimal. The resulting decimal can either be terminating, or it will have a digit that repeats, or a block of digits that repeat. Terminating decimals can be expressed with denominators of 10, 100, 1000, 10,000, and so on. To find the denominator, observe the last digit to the right of the decimal point. The place value of this digit will indicate the denominator. So express each terminating decimal as a quotient of integers. So because the last digit is in the 10ths place, that means that the denominator is going to be 10. So you write the number that's after the decimal and you put it over the 10. And since 7 and 10 can't be simplified because they're relatively prime, we would just leave it as is. The next one, the 9, which is the last digit, is in the 100ths place. And so we put 49 on the top, and on the bottom we put 100. And these don't have anything in common, they're relatively prime. And so we just leave the fraction as 49 over 100. For the last one, the 8 is in the 1000ths place. And so we put 48 over 1,000. Now we need to find their greatest common divisor, which ends up being 8. So we're going to do 48 divided by 8 over 1,000 divided by 8, which ends up with 6 over 125. What about repeating decimals? So these take a little bit more work. So I want to express 0.6 repeating as a quotient of integers. So the first thing you want to do is you're going to let n be 0.6 repeating, so that n is equal to 0.66666 forever and ever. Because the 6 is in the 10th place, we're just going to do 10 times n, but that's 10 times 0.66666. And what ends up happening when we multiply by 10 is the decimal gets moved one spot to the right. So we end up with 6.666666 repeating. Now that we've done this, we want to come over to the other side. We're going to take our 10n, which is equal to 6.66666, and we're going to subtract regular n, which was 0.666 repeating. Well, 10n minus n gives me 9n, and 6.66666 minus 0.66666, all of these 6's are going to cancel past the denominator, and we really have 6 minus 0, which is 6. We want to get n by itself, so we're going to divide by 9. And n, which we had already labeled as 0.6 repeating, is 6 over 9, which we can divide 3 out of the top and bottom. That's the greatest common divisor. And we end up with 2/3. So 0.6 repeating is 2/3. Let's try another one, but first let's talk about the procedure that we just did. You're going to let n be the repeating decimal. You will multiply both sides of the equation in step 1 by 10 if only one digit repeats, 100 if 2 digits repeat, by 1,000 if 3 digits repeat, and so on. You'll subtract the equation in step 1 from the equation in step 2, and then you'll divide both sides of the equation in step 3 by the number in front of n, and then solve for n. So let's try this with 0.53 repeating. The first step is to let n be 0.53 repeating. And so that means that n is 0.53, 53, 53, so on and so forth. Because we have two numbers that are repeating, we're going to multiply n by 100. When you multiply by 100, you move the decimal place 2 spots to the right. So we end up with 53.5353 repeating. Now going to the other side, we take 100n, which is 53.5353, and we subtract the original n, which was 0.5353 repeating. So 100n minus n is going to give me 99n. And just like in the last one, anything after the decimal is going to cancel, which is the point. And we just have 53 minus 0, which is 53. We want to get n by itself, so we are going to divide both sides by 99. And so n is 53 over 99. And we can't simplify that anymore, so we can just write 0.53 repeating is equal to 53 over 99. Now what about when we multiply rational numbers? The product of two rational numbers is the product of their numerators divided by the product of their denominators. So a over b times c over d is just a times c over b times d. We multiply across the top and we multiply across the bottom, and then always reduce to lowest terms if possible. So for example 8, we have 3 over 8 times 5 over 11. We multiply the tops, so 3 times 5, over the denominators, which is 8 times 11. So on top we have 15 all over 88, and that cannot be simplified. Negative 2/3 times negative 9 over 4. So multiplying across the top, we've got negative 2 times negative 9 all over the denominator, which is 3 times 4. And so negative 2 times negative 9 is 18. And 3 times 4 is 12. We can simplify this a little bit. The greatest common divisor between 18 and 12 is going to be 6. So we want to divide the top and bottom by 6. And so we end up with 3 over 2. Three and 2/3 times 1 and 1/4. So if we are given it in this form, we have to transform it into improper fraction form before we can multiply. So let's go ahead and do that. We have 3 and 2/3, which is 3 times 3 plus 2 all over 3. That's 9 plus 2, or we get 11 over 3 for the first one. And we want to do the same thing for the second one. We've got 1 and 1/4. So that's 4 times 1 plus 1 all over 4. Or 4 plus 1 over 4. And we get 5/4. And so now that I've converted them, I can multiply them. So 11/3 times 5/4. We get 11 times 5 on the top, and we get 3 times 4 in the denominator. And so we end up with 55 over 12. You can convert this back to the other form if you want to, but most of the time in math we leave it in this improper fraction. So if you wanted to convert part B back, you would end up with 1 and 1/2. And if you wanted to convert C back, you would end up with 4 and 7/12. Two numbers whose product is 1 are called reciprocals or multiplicative inverses of each other. And so this is going to come in handy when we talk about dividing rational numbers. The quotient of two rational numbers is the product of the first number and the reciprocal of the second number. So if I have a over b divided by c over d, we're going to do what I call keep, change, flip, or KCF. You keep the first fraction the same, you change division to multiplication, and then you flip the second fraction. So for the first one, keep, change, flip, we keep the first fraction the same, so 4 over 5. We change division to multiplication, and we flip the second fraction. Once we've done that, this just becomes a multiplication problem, and we have 4 times 10 over 5 times 1. We have 40 over 5, which is just 8. For the second one, we go ahead and keep the first fraction, -3/5, the same. Change division to multiplication, and then you flip the second one. So we have -3 times 11 over 5 times 7. We end up with -33 all over 35, which is as simplified as that gets. The same thing is going to happen with part C, but we need to convert them first before we can do the keep, change, flip. So 4 3/4 is 4 times 4 plus 3 all over 4. Well, that's 16 plus 3 all over 4, or we get 19 over 4. And 1 1/2 is 2 times 1 plus 1 all over 2, which is 2 plus 1 over 2, or we get 3/2. So using keep, change, flip, we've got 19 over 4 is going to stay the same. We change division to multiplication, and we flip the second fraction. So we have 19 times 2 over 4 times 3. That's going to give me 38 over 12, which we can simplify. We can divide a 2 out of the top and bottom. And we end up with 19 over 6. And if you wanted to convert this back to the original form, that's going to be 3 1/6. Now, adding and subtracting rational numbers is a different story. So the sum or difference of two rational numbers with identical denominators is just the sum or difference of the numerators over the common denominator. So to add or subtract, we have to have a common denominator. Once we have a common denominator, we just add or subtract the numerators. So let's look at 3/7 plus 2/7. Well, we have the exact same denominator, which just means that we add them together, 3 plus 2, and we put it over the common denominator of 7. And so we end up with 5 over 7. Same thing goes for the second one. We already have a common denominator, so we're just going to subtract the top, 11 minus 5 over 12. Well, 11 minus 5 is 6. And we can divide out the greatest common divisor between the top and bottom, which is 6. And so we end up with 1/2. The first thing that we need to do for the last one here is we need to convert this to an improper fraction. So -5 and 1/4. Don't worry about the negative until the end. So we have 4 times 5 plus 1 all over 4, which is going to give me 21 over 4. And then you just want to make sure that you put the negative back up front. And the same thing for -2 and 3/4. We have 4 times 2 plus 3 all over 4, which gives me 11 over 4. And then we just need to put that negative back up front. And so what we end up having is -21 over 4 minus -11 over 4. We have the same denominator, so we have -21 minus -11 all over 4. And those double negatives are going to turn into 2 positives. So we end up with -10 over 4. And we can simplify this by dividing out the greatest common divisor, which is 2. And so we end up with -5/2. And if you wanted to convert this back, which you can, you would end up with -2.5. If the rational numbers to be added or subtracted have different denominators, we use that least common multiple we've talked about of their denominators to rewrite the rational numbers. The least common multiple of the denominators is called the least common denominator. So find the sum of 3/4 plus 1/6. I need to make the denominators look the same before I can add them together. What can I make 4 and 6 both look like? We can make them both look like a 12. So if I multiply 4 by 3 on the bottom, I need to multiply it by 3 on the top. And to make 6 look like 12, I'm going to multiply it by 2 on the bottom and the top. And so we end up getting 9 over 12 plus 2 over 12, which is 11 over 12. Let's try a subtraction problem. 1 over 15 minus 7 over 24. So this one's a little bit harder. I'm not sure what I need to multiply 15 and 24 by, to get their least common multiple. So let's go ahead and find that. The last example was a little bit easier to see. So the first denominator we're looking at is 15. Well, 15 can only be broken apart into 3 and 5. But 24 can be broken into 4 and 6. And 4 is 2 and 2, and 6 is 2 and 3. So 24 is 2 cubed times 3. And so we need to find the least common multiple, which is really just the least common denominator. So remember, we have to take all of the factors. So that includes 3. We've got 5. And we also have the 2. So we bring 2 cubed, we bring 3 to the first, and we bring 5. Well, 2 cubed is 8, and 8 times 3 times 5 is 120. So that is what I need to make both of my denominators look like in order to combine them together. So 15 times what is going to give me 120? Well, 15 times 8 will give me 120. And what I do to the bottom, I have to do to the top. And 24 times what would give me 120? 5. And so what I end up having is 8 over 120 minus 35 over 120, and 8 minus 35 is negative 27. And then I want to see if I can simplify this. So the greatest common divisor of 27 and 120 is 3. So we can divide 3 out of the top and bottom. And so we end up with negative 9 over 40. Now, order of operations still applies with rational numbers. So let's go ahead and try example number 13. As a reminder, this is PEMDAS. And so the first thing we want to do is simplify the parentheses first. So we've got 1/2 cubed minus, we need to have a common denominator. So to make 2 look like 4, I'm going to multiply the bottom and top by 2. So I have 1/2 cubed minus 2 over 4 minus 3 over 4 squared times negative 4. And so when I combine, I end up with 1/2 cubed minus negative 1/4 squared times negative 4. That takes care of the parentheses. The next thing is going to be my exponents. So I need to simplify those next. So 1/2 cubed and negative 1/4 squared. So remember, all we do is we are going to bring the power to both pieces. So 1 cubed is 1, and 2 cubed is 8. Negative 1 squared is 1, and 4 squared is 16. That takes care of the exponents. The next thing is multiplication and division, which happen on the same step. And the only multiplication I have going on here is negative 1 over 16 times negative 4, which we just multiply across the top and bottom. So we have 1 over 8. Negative 1 times negative 4 is positive 4 all over 16. And then the last thing is addition and subtraction. And what we have to have is a common denominator so that I can combine these two. But luckily I can make 8 look like 16 by multiplying by 2. So I have 2 over 16 plus 4 over 16, which gives me 6 over 16. And then we want to simplify. So the greatest common divisor is 2. So 6 divided by 2 over 16 divided by 2 is going to give me 3 over 8. And that is my final answer. The density of the rational numbers just says that it is always possible to find a rational number between any two distinct rational numbers. Mathematicians express this idea by saying that the set of rational numbers is dense. So if r and t represent rational numbers with r less than t, then there is a rational number s such that s is in between r and t. So find the rational number halfway between 1/2 and 3/4. So what we need to do is add them together and then divide it by 2. We're just finding the average between these two numbers. So 1/2 plus 3/4. We need to have a common denominator, but we can make 2 look like 4 by multiplying by 2. And so we have 2 over 4 plus 3 over 4, which gives me 5 over 4. And then we want to divide this by 2. So 5 over 4 divided by 2. Remember that we can always write a denominator of 1 if it's not there. And so we're going to use keep, change, flip. We keep the first, change division to multiplication, and flip the second. And we end up with 5 times 1, which is 5, over 4 times 2, which is 8. Which is in between 1/2 and 3/4. And the last one, a chocolate chip cookie recipe for 5 dozen cookies requires 3/4 cup of sugar. If you want to make 8 dozen cookies, how much sugar is needed? So let's go ahead and write some stuff down. The amount of sugar needed is the desired serving size divided by the recipe serving size times the ingredient amount in the recipe. So if I want to make 8 dozen cookies, that's my desired serving size. We've got 8 dozen on top, divided by the recipe serving size, which is for 5 dozen, times the amount that is needed of that ingredient, which is 3/4 cup, and so this is just a multiplication problem. We've got 8 times 3 on top over 5 times 4. This gives me 24 over 20. And we want to divide out the greatest common divisor, which is 4. And we end up with 6 over 5, which I am going to convert back, and that's 1 1/5 cup of sugar that's needed for my new recipe.